let's look at a more abstract Euclidean algorithm, Diophantine equation problem. So let a be a fixed positive integer, and a is going to be greater than 3 just to avoid some special cases that are a little bit different. And we're going to consider an equation of the form ax plus a plus 3y equals 1. So this is a whole family of equations. Like it could be 12x plus 15y equals 1, could be 13x plus 16y equals 1, could be 14x plus, that's supposed to be a 17y equals 1, or 298x plus 3y equals 1. I want to see what's in common with these equations, although they're not all going to have the same behavior. And I wanted to do it as much as possible with just having a be a letter and do it in general, because it's a nice little up in the level of challenge and abstraction. So the first question, the first task is, suppose a is a multiple of 3, show that ax plus a plus 3y equals 1 has no solution. Okay, so there's various ways to do that, but we can always just hit it with Euclidean algorithm, apply the Euclidean algorithm to the pair a plus 3 and a. Doesn't take too long. A plus 3 is going to be 1 times a plus a remainder of 3. Okay, and we know that a only goes in once because of this restriction that a is greater than 3. Okay. Okay, so then a equals, oh hey, now a is supposed to be a multiple of 3, so a is like 3q, let's say, plus 0. We're done. And of course, as shouldn't have been too much of a surprise to anyone, the GCD of these guys is 3. Okay, and of course, that means there's no solution. So the GCD of a plus 3 and a here is 3, so no solution. So no solution. Now, there's only two other cases. A could be 1 more than a multiple of 3 or 2 more than a multiple of 3. That's what the division theorem says. I'll just have us do 1. You can do the other one yourself if you want. So now suppose that a has remainder 1 when divided by 3. Now, let's show that ax plus a plus 3y equals 1 does have a solution, and I want to find it explicitly in terms of a. Okay, so this will be a general formula for this family of cases of a linear Diophantine equation. Okay, so now let's apply the Euclidean algorithm. Again, the first step is the same, 1 times a plus 3. Okay, but now a is going to be 3, let's say q for quotient, plus, and we've assumed that it has remainder 1, and so that's going to be 3q plus 1. Okay, so now that 1 tells us that the GCD is going to be 1, and it tells us, okay, now we can do set up the backward steps where we solve for the remainders. Okay, so this says 3 is, no surprise, but I'm going to make it really explicit, 1 times a plus 3 minus 1 times a. Okay, so it might seem really silly to write 3 in that complicated way, but that's exactly the analog of what we were doing in the previous example with the numbers. Okay, so now a equals 3q plus 1 is 1, means 1 equals 1 times a minus 3 times q. Okay, now let me just remind ourselves, q is none other than a minus 1 over 3. Okay, we tend not to use division a lot yet in this process because division has the danger of always taking us out of integers. This is where we live usually for number theory. But we know that a minus 1 is divisible by 3, and that quotient is just that guy. Okay, so if we want to express q in terms of a, we can do that. For a lot of purposes, it's going to be good just to leave it as q. We just know there's some integer that that's true for. Okay, so now I just have to combine those. So 1 equals 1 times a minus 3 times, now what was q? Well, sorry, 1 times minus q. Now what was 3? It was this guy. I'm just going to copy and paste it. Cheat a little bit. Okay, and now I'm just going to collect again. So notice it's exactly the same scheme, but you have to just deal with the letters as well. Okay, so now how many factors of a? I want this to be something, we'll put it in, something times a plus something times a plus 3. Okay, so what is in front of an a here? There's a 1 in front of an a, and then a minus q times minus 1 times an a. So that's going to be q plus 1 times a plus, oh, minus, okay, and then the rest of it is just a q times a plus 3. Okay, so the claim is that the pair x and y equals q plus 1 and minus q solves this equation. Okay, let's check that. Okay, let's check it. I don't want to make the video too long. If you believe it, then you don't have to watch the rest of the video. Let's just check it a couple of ways. One is, let's do 13x plus 16y equals 1. Okay, so the claim here, so q, well, let's see, q is the smaller of the two numbers, minus 1 divided by 3. So that's 13 minus 1 is 12 over 3 is 4. Okay, so the claim is that xy equals 5 minus 4 satisfies the equation. Well, we can test that. 13 times 5 minus 16 times 4, you bet. 65 minus 64 equals 1. So that's some evidence that it's true. Okay, you could even do a more hardcore proof. Oop, I lost my stuff here. Okay, by just substituting in the q and doing some good old-fashioned algebra. Okay, so q minus 1, that's, or q plus 1, that is a minus 1 over 3 plus 1. That is, I don't need that, a minus 1 over 3. Okay, put that over everything over common denominators. You've got a minus 1 over 3 plus a 3 over 3, so that's a plus 2 over 3 times a, minus, that's going to be the quantity a minus 1 times a plus 3 over 3. Common denominator, you get a plus 2 minus a minus 1, a plus 3 all over 3. And if you FOIL it out and expand, then indeed it all cancels to 3 over 3 equals 1. I'll let you do that if you want. So interesting how algebraic it gets when you force yourself to check it in general. It gets to like polynomials and stuff like that, and rational functions kinds of algebra. Haven't done that in a bit. Okay, so this is an example of how it can get rather more interesting when you start to generalize, as it usually does. But it turns out that if you do this, you take the quotient of a divided by 3, just throw away the remainder, add 1 and negate it, then that will actually solve this original equation.